chaos, horseshoes, transverse, there's going to be a lot of stuff. Clinic. Orbits.
Yes. You wouldn't know that the person was named a T.
And
that's off the last. I know someone else who is off the UR. But you notice my name came.
Well, I think the sort of stimulus for modern chaos theory can be traced back to Edward Lorenz. He was not a mathematician, he was an engineer, fluid dynamics person, who in 1962, about 61, was looking at an atmospheric model for atmospheric fluid flow. So you have fluid, you have temperatures, and he developed a very simplified ordinary differential equation model for this system of PDEs. System of PDEs typically Navier-Stokes equations, heat equations, continuity equations, and this is what he came up with. See if I can remember. X dot is equal to sigma minus x plus y. Y dot is equal to, see, I always forget.
I can read the book if you want.
No, I have it here. That's why I have my notes. Yeah, I was right. But not. E dot is equal to minus ey plus xy. Does that work? It does indeed. Here's a very simple model. There are some standard kinds of parameters in here. Sigma is the so-called Prandtl number. R is or Reynolds number. And B is some sort of a geometric parameter. Okay. Well, the equation is roughly linear, except for these. Is that correct? Yeah, okay. I got myself. Roughly linear, except for these nonlinear terms. So Lorenz was not really an analyst. He was really solved these equations using typical Runge-Kutta technique. He figured, the story goes late in the evening, he got this, he coded the thing up, and he figured, well, he'll come back the next day and he'll have all these plots of solutions, wonderful plots. Problem is chaos. You looked at the numerical output, it was jumbled, it looked random. Why should that happen? Perfectly good, standard differential equation solver, a simple system of three ordinary differential equations, mostly linear terms, except for these two. Why should this produce these results? Of course, he thought, well, maybe I'll have to check the code. He looked it over, checked it twice, 3 times. It was correct. So something was definitely going on here, something odd. And this is kind of where the notion of chaos was born. Chaotic solutions, unpredictable, random, hard to solve for numerically. So what did he find after he perfected his program a little bit? he was able to actually plot some solutions of this thing. Now, it turns out that if you take, what is it? If you take sigma is equal to 10, Prandtl number 10, B is equal to 8/3, and let's say that R is greater than 24.75, what do the plots look like? Once he was able to get some reasonable looking plots. Well, let's see if I can draw the Lorenz butterfly. Here's the z-axis. This is always a challenge for me. This is, let's say, the x-axis. This is the y-axis. And if I look at these plots, how do they go? They sort of all kind of converge in here. We got this thing, it's like this thing here. I got this thing, it's like a wing over here. If you follow these trajectories, they seem to be heading into what looks like a sink. If I come over here, they're going the other way around, kind of. And things are going in like this. They seem to be, and this thing just keeps going around and around and around. It sort of goes like this. So if you start in a position here, it winds around for a while, and then it goes to the other wing of the butterfly, winds around for a while, then flips back to this wing of the butterfly. It goes round, and as a matter of fact, not only did you get this kind of unusual sort of steady state position, steady state picture, but this thing is actually an attractor. It's not a point. By attractor, what I mean is actually a global attractor, that if I started off somewhere here and I plotted the trajectory, eventually the trajectory would kind of wind into the butterfly. So it attracts all nearby points. So the fluid is going to go around in this kind of crazy way. This is going around and around, and back and forth and back and forth. And this is the Lorenz Strange, chaotic attractor.
Page 320 has a picture of it too.
Better than mine, I'm sure. Better than mine, I'm sure. Anyway, well, okay, it's an attractor. So all trajectories starting out in the three-dimensional space will eventually wind into this back and forth kind of butterfly situation. And if you look at this, if I took a microscope and I looked at, let's see, it's micro. If I looked at, say, put my eye right here, I would see things that kind of look like this. Not nice little things, but things that seem to look like this. And if I actually increase the scale of this thing in a more powerful microscope, say I focus here, it looks like I'm going to get a smaller version of the same thing. This is the scale of the thing. So this set is not the usual kind of set you see in geometry. It is what's called a fractal set. It has a dimension, not a regular dimension, a dimension which is fractional. So the strange means that the attractor is fractal. Okay. We know what attractor means. What about the chaotic part? Well, the chaotic part means that as I follow this around, points that start close to one another will rather rapidly separate. In other words, there'll be sort of very initial condition. That is, if 2 points start very close to one another, in a fair amount of time they'll start getting quite far from each other. So it's very hard to predict how nearby points are going to wind up. Now, this is a very simplified model of weather in a way. So if this is a simplified model, the full models that the meteorologists use are going to be a lot more complicated. They're going to be chaotic as well. And is it any wonder that the weather is so hard to predict many days in advance? It's just naturally chaotic. You cannot predict the weather, no matter how good your machines are, your computers are. You're not going to be able to get an accurate prediction of weather for more than 5 or 6 days at best, because there are these strange Lorenz-like attractors in here. Well, once these things sort of hit the mathematical community, a lot of people got interested in this because of the very interesting attractor and the fact that the system is so simple. A lot of people started saying, well, if it looks like a strange attractor, well, maybe I can prove it's a strange attractor. And there's a book by Sparrow where he looks at lots of cases and is able to prove for certain parameter ranges you do indeed have a strange attractor. How does he do that? Well, there are typically 2 ways of doing it. There's a geometric way of trying to find what is called a horseshoe. I'll draw a picture of that in a minute. And then there's also this method of Melnikov, which has become quite popular for finding transverse intersections of stable and unstable manifolds. Anyway, so that's a little bit of a lead-in. Here's a pretty picture. Okay, 1963, kind of the birth of chaotic dynamics. Well, here's one way of getting a handle and proving, let's say, that for certain parameter values. Look at my little picture over here. One way to prove chaos. And also strangeness is to find horseshoes. Oops, we're going to need horseshoe maps. Well, what Sparrow has done is, you know that if you have, let's say, a dynamical system in 3-dimensional space, especially one that's recurrent, as this is, because it keeps coming back over and over again to roughly the same place, is to find a transversal surface. So, for the right, well, you've got to find it. Search around, get just the right transversal. For the right transversal surface, the Poincaré map behaves as follows. Okay, so here's my little transversal. I find it over here. It's a nice little surface. And what I do is I follow the trajectories around until I return. It's the first return map. Here's the map, Poincaré map. And it turns out that there are regions in here that look like this. If I start out with something that looks roughly like this, sort of like a little trapezoid, curvilinear trapezoidal shape. Let's call this Q. Okay. And then I look at the image of this. I actually look at the image of this. The image looks something like this. This is P of Q. And this, my friends, is the horseshoe. And you can see why it's called. It looks like, it actually looks a little bit more like a boomerang than a horseshoe. But it takes this, basically the square thing, it squeezes it in one direction, it extends it in another direction, and then it turns it around so that the image looks like this. And I can focus on the intersections, the successive intersections of p squared of q, p cubed of q. And by studying this, I can actually prove chaos, fractal, etc. Well, etc. What are other signs of chaos? You know something, you're familiar with Strogatz, the Lyapunov exponents. If the Lyapunov exponents are greater than 1 and a couple of other conditions are sort of in play, then you know that you have this large dependence on initial conditions, and that kind of leads to chaos, and a lot of other things as well. So here we see Lorenz, the differential equations, Poincare map, which is now sort of just a planar mapping. It's just a 2D mapping, and it has this horseshoe-like property. I want to examine these things in more detail. Once you have the horseshoe, you have sort of the game is over. You know exactly what's going to happen in terms of the long-run behavior of this thing. All right, so, well, a few years later, Idon, in hopes of being able to get a better handle on what the Lorenz map was doing, formulated this simplified model of the Poincare map, or Poincare map of this type. So this is the so-called Idon map. Approximates P for Lorenz equations. And he came up with an extremely simple form. It's a map, let's call it H, from R2 into R2, which looks like this. H of xy is equal to A plus BY minus x squared, comma x. Very simple looking map of the plane. For the right values of A and B, I forget exactly what the values are. Let's see, maybe I remember.
Well, they actually have to do that on their midterm.
Okay. Let's see. If A is equal to, what is it, 1.2, and B is equal to 0.4, the map behaves this way. So let's look at the image. So we're in the XY plane. This is roughly 2, 2, 2, okay. If you take a trapezoidal kind of cube, something like this, okay. And we call this Q now. Let's look at the cube inside. It's getting a little busy in here, so let's say that this is Q. If you look at f of Q, this is h of Q actually, and here's your horseshoe. Idon introduced this map, played with it, simulated it, saw that you get chaos. It's kind of interesting looking chaos. It's truly kind of boomerang shaped. So it goes back and forth. kind of like that. So you have an attractor, it's a global attractor, and again, it's going to be strange. It's going to be Cantor set-like, it's going to have a fractal dimension, and this is the famous Idon attractor. Quite a few years later, by dint of an amazing amount of very, very precise analysis, it was actually proved that this is a strange attractor. And that result really gave birth to a whole field of study about certain kind of attractors. This is called a rank 1 attractor. And people have been working on rank 1 attractors, etc. Actually, I'm working on this thing as well, proving that this thing is a strange attractor with some techniques that we've developed that will make the proof of the original proof a lot shorter. Still a little tricky. You still have to carefully monitor how the map works geometrically. But it turns out essentially that there's a point here, let's call it a point P. It's going to be a saddle point, and if you follow the unstable manifold at this saddle point, the attractor is actually equal to the closure of the unstable manifold P. You characterize it, and since it's kind of like an extended one-dimensional thing, it's called a rank 1 attractor. All right, head on, nice stuff. Well, that was sort of the fun part because it was all sort of pictures and vague qualitative statements. What I want to do is I actually want to get into the analysis of things like this a little bit more closely, and in particular exploit a way of representing the dynamics of mappings like this in terms of sequences and so-called ship maps on sequences. Okay, so transverse homoclinic point. Okay, so here's an unstable manifold right here, and there's going to be another fixed point here, so that the stable manifold actually, the stable manifold of this will actually intersect the unstable manifold. So if you've got kind of a situation that looks like this, let me sort of blow this up. Here you have a saddle point, okay, like so. And if I follow the unstable manifold around long enough, it actually comes back and intersects here. So here's stable, here's unstable, and notice that this intersection is transverse. This is called a transverse homoclinic orbit. Let me say a little bit more about it. I'm going to blow it up and examine it a little bit more closely. So let's take that picture. Let's bring it over here. So here's the point P. Okay, stable, unstable. And here's your transverse homoclinic point. Why should transverse homoclinic points lead the case? By the way, this goes back to the early 1900s. This phenomenon was actually discovered by Poincaré, who, although he was brilliant, did not have the tools to fully understand what was going on, but he had a good inkling. Why is this going to be kind of an interesting point? Well, let's see. What happens to this point? Well, it's on the unstable manifold and the stable manifold. So what this is going to do, as it moves along the stable manifold, it's going to bring this back. There's going to be another intersection. It's going to keep going like this. Another intersection, another intersection, another intersection, and closer and closer and closer. And you can see basically why you're going to have chaos, because you're going to have this rapidly oscillating manifold. It works the same way here. This is also, of course, a point on the unstable manifold. So if I go negative time, it's going in this direction. And you get this whole series of transverse intersections. You'll get actually a whole continuum of these intersections. So transverse homoclinic orbits would seem to indicate, seem to be some signal that you could use to actually see chaos, expect chaos, and maybe even analyze the chaotic motion. All right. And it also gives birth to symbolic dynamics. Okay. So what I want to do is I want to revisit an example that Amin did a while ago with the doubling map, mod 1. I want to re-examine it and exploit its properties, first of all in terms of graphing the iterates, and secondly, in terms of recognizing that the map is equivalent to a shift map, right, on sequences 0 and 1. Okay, so this is sort of in there. What about the symbolic dynamics deal? So let's call this 2x mod 1 revisited. So we're looking at a map, F, from 0, 1 into 0, 1, okay? Where x goes into 2x mod 1. Okay? The doubling map. Well, first of all, let's see what we can say about periodic points and some other things for this map without looking at the symbolic dynamics. So let's see. What does the graph of F look like? There in the unit square. You have it. Okay. Like that. So that's F. If I want to find the fixed points, I want to find the intersections of the graph with the line y equal x. Where's the fixed point? Well, it intersects the graph here, and it intersects the graph here. Only these 2 points are the same, mod 1. They're both 0, right? So x equals 0 is the only fixed point. Well, let's look at f squared. Well, what is f squared? F squared of x is equal to 4x mod 1. Well, this thing is self-similar. In other words, I put this here. So this picture will be reproduced in half of this square, just like this. Picture is not beautiful. Okay. What about now the periodic points of period 2 as compared to the fixed point? Well, I know where the fixed points are. So if I draw, I'm using for my y equal x. Okay, so that's my y equal x. So let's see. Well, it intersects here and here, but that's nothing new. That's just the fixed point. But notice that it also intersects the graph here and here. And what happens is, if I take the image of this under f squared, it goes to here, and then it goes back to here. So in this case, these 2 points, let's call them P and Q, form what's called a 2-cycle, where f squared of P is equal to P, but f of P is equal to Q. So in other words, it is a fixed point of f squared, but not a fixed point of f. So it's a true period to periodic point. Okay. So I know that the dynamics of the 2x mod 1 map have fixed points. They have periodic points of period 2. What else? Well, let's keep it up. Not too much longer. What's there? So how about f cubed? Well, it just rescales this thing. In other words, it takes this picture and it squeezes it into the left half. That may be a little tricky to do. Let's see. 1, 2, 3. 1, 2, 3. So it goes like this. Okay, same picture here. Well, f cubed of x is equal to 8x mod 1. I claim that this thing has periodic points of period 3. Well, let's see. Fixed points, yes. They're the fixed points. Now, there are also these 2 points, roughly over here, sort of here, P and Q, sort of, okay, so there's P and there's Q. These are period 2 points. Well, there are more intersections. There's this, there's this, there's this, and there's this. Okay. So what happens is you actually get a 3-cycle. Well, there's a famous paper by York and Lee that says period 3 implies chaos. This is a 1-dimensional map. It has a period 3 point. I can just forget about the rest of it and say, therefore, it will have periodic orbits of all periods. But I don't have to. I don't need Lee and York's theorem. I can just keep repeating this. Look at F4, F5, etc. Just keep squeezing this, right, by half, the picture half each time. I see by this picture that F has periodic points of all periods. That's just done from the picture. But there are some other things that you can't see very well from the picture, like the following. There's actually, you can prove that there is a dense orbit. In other words, if I take some point, starting point, and I look at f of x, f squared of x, f cubed of x, that point wanders around within the line from 0 to 1, and it fills up the entire line basically. In other words, the set of all points will be a dense subset of the unit interval, so that the closure is equal to the whole unit interval. You could, by really, examining the heck out of this, sort of show that there's a periodic, that there's a dense orbit, but it's difficult to show from the pictures. There's an easier way. This map is equivalent to a symbolic map shift, as I think I mentioned last time. Maybe not. I think he did. Let's re-examine this map. Let's represent this. Okay. Well, let's see. We know that every real number in the unit interval has a binary expansion. The coefficients are between 0 and 1. It's a property of the completeness of the real numbers. Okay. I can actually, I sort of know what these denominators are. I can simplify the representation of this point as an infinite sequence of zeros and ones. I can identify x, let's say, with s equal A1, A2, A3, etc. Okay. So what is the sequence? The sequence is a map from the natural numbers into 0 and 1. So for every I'm sorry, 0, 1. That's 1. Okay. And therefore, I can represent this map symbolically. Well, symbolically how? Let's see. So if f of x is equal to 2x mod 1, right? And I'm going to multiply the series by 2. Okay. So that this takes A1, A2 into A2, A3, A4. In other words, this is a shift map. Think of this thing as being, let's say the decimal is here. A1, A2, A3, shift map moves the decimal one place to the right. Okay? So the 2x mod 1 map can be represented as let's see, a set of all sequences. So F can be identified with sigma mapping the set of sequences, a binary sequence is, this is sometimes called 2n into 2n, where sigma of A1, etc., A2 goes into A2, A3, blah, blah, blah. Okay? So for all intents and purposes, I can take this, it's not a continuous map, it has a discontinuity, right? I can represent this map by just a mapping of symbols, a shift map. This is called the shift map. Well, what's so great about that? Well, once you have this representation, all of those properties that I mentioned that we could derive from the graph by looking closely at the iterates become rather trivial. Okay, so the 2x mod 1 map is a shift map on the binary representation of the real numbers. By the way, since I'm dealing with x equal to some k equal 1 to infinity, a sub k over 2 to the k, then I'd like to define a norm, a metric, solely in terms of the binary representation. How can I do this? Well, I can define, let's suppose x is a1, a2, and y is equal to b1, b2, etc. If I'm going too fast, slow me down, slow me down. When I get rolling, I'm unstoppable. No, I'm not unstoppable. Okay. I'm going to define a new metric, which is basically equivalent to the absolute value of the difference between these 2 points. Let's call it, I'll say sub s for the symbol metric. And this is equivalent, this is basically equivalent to the usual absolute value. Just plain x minus y, absolute value of the difference. Why is it? I'm not going to go through a detailed proof of it. Why is this metric the same as this one? When this is close, and vice versa. Well, if x and y are close, their binary expansions are going to agree up to some point rather far out in the sequence, right? So all of the initial coefficients of the 2 have to be basically 0, right? They're basically 0 or 1. It's only those terms beyond, well, let's say k is greater or equal to n. But when k is greater or equal to n, I know because 1 over 2 to the k is a uniformly convergent series, that gets smaller and smaller, right, as I go further and further out. So saying that this is small means that the first few initial ones have to be the same, and they may differ from some point, capital N on out, which means that the actual real points are close to one another. So closeness in terms of this metric is basically the same as closeness in terms of the absolute value metric, or absolute value difference. Okay? So I can work totally in this space with the metric S. So 2n with this metric, is actually a normed space. It's a metric space. Let's not worry too much about algebraic. It's a metric space. It makes the space of these maps, sequences, it makes it into a metric space. Metric space is a space that has a metric dxy. dxy is equal to 0 if and only if x is equal to y. dxy, or dxz is less equal to dxy plus dxz, the triangle inequality, all those usual properties. This thing has those fine. It's a perfectly good metric for the space of symbols. All righty. What about the dynamics? That's what we're mainly interested in. Okay, let me show you that I have periodic points of all periods for the shift map. Well, let's see. Start out with A1, A2, through AK, and repeat it. A1, A2, AK, and keep on repeating this. Look at the sequence where I have the first K of these coefficients repeated. Okay? This is conveniently represented by this symbol. It's very useful. AK bar, which means just keep repeating A1 through AK. What do you know about F sub K of A1 AK? It's equal to A1 A2, AK. So it takes all repeating representations. Well, you don't want them all to be the same naturally because then you'll have a smaller period. So you want to make sure that this is such that f of j of A1 through AK is not equal to A1 through AK bar for j smaller than k. So you want it to be the least period. That's easy to do. You just have to make sure within the k there are no smaller periodic things going on. So from the symbolic dynamics, it's clear that this has periodic points of all periods. What about the dense orbit? The dense orbit. Well, here's something that I'm just going to sketch for you, and I'll give this as kind of a homework problem for you to work out the details. Sort of fill in the shift map has a dense orbit. Well, what I want to do is show that if I take a high enough iterate of f, I can make it as close to any point on the unit interval as I want. Well, how might we do that? Find the right initial point. Okay. Well, now I'll consider truncated representations of the sequences with all of the possible permutations of the ones and zeros in there. So let's see. Well, what about all possible one? So this, right? And we could repeat that. That's not very interesting because basically it'll give you zeros and ones. Okay, so that's all possible ways of taking, let's say, 2. So you could have 1, 0. The other possibility is 0, 1, and 1, 1. So notice that this thing, if I take an iterate, it will enable me to represent any, what did I just do? Yeah. So if I look at this, let's focus on this. So 2 iterates will give me 1 into 0 or 0 into 1. So I'll be able to match the first 2 coefficients with just this, right? 1 iterate, shift map goes over here, so the first one becomes a 0. Now, so that takes care of all of the permutations of zeros and 2 zeros and 1s. Okay, now let me consider the permutations of all 3s. I forgot 1, right? I forgot 1, 1. Okay. So after I do 0 and 1 and 1 and 0, so 0 and 1, 1 and 0, okay, but there's also 1, 1. So if I go far enough out, if I take enough iterates, I can make the first 2 be, well, 0 and 1, or 1 and 0 and 1 and 1, which takes care of all possibilities for A1 and A2. Now what I want to do is I want to string on this, right, all possibilities for the first 3 coefficients. Well, it could be, how many possibilities are there? 8, right? 2 to the 3. So there's 0, 0, 1, 0, 0, 0, 1, 0, there's 3, 0, 0, 1, blah, 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 and then winding up with this. So that's the set of all permutations of 0 and 1. So if I go far enough out, I can match any first 3 coefficients for any point in the interval. So what shall I do? Well, keep it up. That takes care of first 3 by a shift. Now I want to take care of all possible permutations of 0 and 1 for the first 4. All right, so there's 0, 0, 0, 0. That's one possibility. How many are there here? 2 to the 4th, 16. There's a lot of stuff to write out, but it's going to end up 1, 1, 1. Okay, that's finished with the first 4. Then the first 5. Then first 6th. And then by stringing them all together, I'll be able to take care of the first k for any k, right? So if I want to be able to take care of the first k, I'll consider the 2 to the k ways of permuting 0 and 1. I will add that on to what I've already done, up to k minus 1. And then after I'm finished with that, I'll paste on the first k plus 1, then the first k plus 2. So what happens here, for this point, it's a rather complicated one. Just think about it, maybe think about the details. Given any x naught belonging to 0, 1, and epsilon bigger than 0, there'll be a k such that fk of x, this special one, let's call it x star, fk of x star minus x naught will be less than epsilon, because it'll agree up to some large subscript capital N. The tail of the series is going to be as small as I want by making the truncation large enough, right? Because we know that 1 over 2 to the k, as k goes from 1 to infinity, is convergent, which means that the tail can be made as small as I want by simply taking k large. Okay? There's your dense orbit. Can I draw it in my little graphs? No, not so much. Very hard to kind of see it from the graphical analysis of the dynamics. But the symbolic dynamics, bingo, there it is. Very nice. This is actually something like a 2-piece Cantor set representation. Why? Because you can think of how this thing maps. Let's say this is 0, this is 1, right? Depending on where you start, you'll end up after a few terms either in 0 or 1. So you can think of it as I look at the iterates. First iterate's going to map into 2 pieces. Each one of these things, because of the scaling property here, is going to produce an image 2 more. And if I look at this here, this looks just like the good old Cantor set. It's a little different because it's kind of a dynamically generated Cantor set. The usual Cantor set, well, you know what the usual Cantor set is. The middle third Cantor set. You'll help me, right? You start out with the unit interval, then what do? Next stage, you throw out the middle third. Okay. Next stage, you throw out the middle third of the remaining pieces. This, and this. And then you just keep repeating the process. The limit of this, as n goes to infinity, is going to be the standard Cantor set, the middle third Cantor set. Can I draw a picture of that set? Not on your life. It's all over the place, right? It's just a bunch of points. It's sometimes called Cantor dust. It's a bunch of points where you can sort of see things. They seem to be accumulating in some way. So you can sort of see a pattern. You can see this sort of fractal pattern, but you can't draw it. It's a very interesting set. It's completely disconnected, right? And interestingly enough, although it seems to be created by just adding more and more points in terms of a countable process, the Cantor set is actually uncountable. It has the same cardinality as the unit interval itself. A very interesting set, and really sort of at the heart of most chaotic dynamic situations, as we'll see shortly. Okay, so if I choose to use symbolic dynamics for this map, I can really analyze the heck out of the dynamics. I know exactly how it's going to behave, what the periodic points are going to look like. Not so much to draw pictures of them, you know, in terms of the graph, but represent them in terms of the sequence of zeros and ones and the shift map. Good. Got that? So symbolic dynamics are good. They're very good. Can you think of anything else that would have maybe interesting symbolic dynamics, something like this, where you maybe have some Cantor set behavior? What about other examples? And this example I'm going to do now is much more like the middle third Cantor set. Interestingly enough, all Cantor sets are equivalent to one another, although they may look very different. They're topologically equivalent. There's a bicontinuous map from one to the other. That's kind of a tricky result. Other examples, oh, okay, so how about f of x equal 3x mod 1. I'd like to understand the behavior of this thing, maybe in terms of symbolic dynamics. Well, what does this look like? Because if I draw the graph, now I divide it into 3, right? So that would be the graph. And you can see here that, again, you will have fixed point at 0, which is the same as 1, right? Mod 1. But there's another one now. So there's another distinct fixed point. Okay? And of course, if I want to draw f squared, I just squeeze this picture, not by half anymore, but squeeze it by a third, and simply repeat it in each of the original things to draw the graph of f squared, then f cubed, and so on. This has periodic orbits of all periods. It also has a dense orbit. What do you think is a possible symbolic dynamics? Representation of 3x mod 1. Well, let's see, 2x, I used binary expansions. There's nothing sacred about 2. 3 is fine. I don't want to use 4 because that's just sort of 2 over again. 5 is fine, etc. I'll use triadic expansions. The completeness of the real number says that every point in the unit interval can be represented not over 2 to the k, 3 to the k, where a sub k is equal to 0, 1, or 2. You can actually use this directly to create the basic Cantor middle third set. How so? Well, you want to create the Cantor middle third set. You just take all representations where a sub k is never equal to 1. They're going to be here, or they're going to give you there. And as you iterate this map, it's going to do the Cantor-like thing, throw out the middle third of the remaining pieces. So taking the shift map, okay, let's call it this, the shift map here, this is just going to be A2, A3, etc. Again, it's a shift map because it's multiplying it by 3. So it throws out the first one, and it starts out with A2. Okay? If I take the iterates of this thing for all x where AK is not equal to 1, then this is going to fill out the iterates. F sub k of x will fill out the middle third Cantor set. So I can describe the standard middle third Cantor set geometrically by this iterative process, or I can define it as the image of the 3x mod 1 map on points which either start here or start here. Okay? That is going to flesh out, it's going to actually comprise the middle third Cantor set. Okay. You like other ones? 5x, 7x. As I say, 8x and things like that, no good if they're divisible by 2 or 3. So you want like primes. And you get a whole host of things that have periodic, of all orders, have dense orbits, which once again are obtained by using the n-adic expansion of these things. Right? N is 2, 3, 5, etc., some prime. Of course, here I would use a different metric. Here I would use some k equal 1 to infinity, a sub k minus b sub k, not over 2 to the k, but over 3 to the k, and that would give me a perfectly good way of measuring the closeness of points in the unit interval. So you can create a whole host of these things. Symbolic dynamics, especially when they're shift-like, is a powerful way of being able to determine certain really important aspects of the dynamics. Good? Well, how else might I get, let me revisit something else. How else might I get a Cantor set, like a two-piece Cantor set, sort of like this? Here's another way. So, how else to find, let's say, F invariant? Cantor sets. Well, there are lots of ways of doing it. Let me show you another way of doing it. I'll do it with a logistic map. I'm going to do this with the logistic. Phi F invariant, I'm saying that F takes this into itself. In other words, it maps the subset into itself. You would say that set is F invariant. Okay, let's take a look at the logistic map. Lambda x, 1 minus x. Okay, so L of lambda maps the unit interval into itself. Well, it depends. Okay, not exactly. Not exactly, because if lambda is bigger than 4, don't forget the maximum of this thing is going to be lambda over 4. So if lambda is bigger than 4, the maximum is actually going to be bigger than 1. The graph then, looks like this. Okay, it's a nice logistic map, but it goes up a little too high. The map would look like this. Now, you know from this polynomial form that once I'm in here, any of these points are ultimately going to go away from the square. They're never going to come back. Okay, so I ask myself, everything in here will be out of the square after one iterate. Let me see about those points which will be out of the square in 2 iterates. Well, what do? I draw this line, right? And then I find the intersections of these things. And when I do, I can define the pre-image of this interval here, and there's an interval there. So then after 2 iterates, I'm up here and I'm out. Let me take the pre-image again. So in each of these pieces, there's a middle third that goes out. So if I consider, let's say, omega to be x belonging to the interval from 0 to 1, such that f of n of x belongs to the square, belongs to 0, 1, for all n. Let's call this set omega. Well, it's certainly going to be invariant, because if I start there, I never go outside the box. I have to stay on it. What is it? Well, let's see. You started out here. Okay, then you threw this away. Okay, so 1 iterates, these are out. Then after 2 iterates, you throw that away, symmetrically. 3 iterates. Hey, this is the usual Cantor set. So using dynamics to identify Cantor sets, invariant Cantor sets in particular, is not hard to do. There's lots of different ways of doing it. One of the most important ways of doing it is in terms of the Smale horseshoe, with also its way of representing things in terms of symbolic dynamics, which I'm not going to show you. All right. There we go. We're going to describe, it's hard to actually draw or represent the mapping that I'm going to picture here in terms of nice functions. So it's easier to just describe the horseshoe geometrically, which we'll do. So let's talk about the Smale horseshoe and its symbolic dynamics. All right, I'll try to draw it reasonably well. Actually, I'm pretty good at drawing on the board, not so much. Okay, so we start, let's say, with a square. Let's call this Q. Depending on what book you look at, let's call it S. So here's the square, S. Let's put a cap on top and a cap on bottom, like so. And now what I'm going to do is I'm going to take a point here. It's going to be a saddle point. What it's going to do is it's going to squeeze everything this way. And expand everything this way. And I'm going to make this go down into here, where this is a nice sink. And I'll set up this mapping so that the horseshoe, what are we going to call it? F. Okay. F, yeah. Here's the horseshoe map. So this is S, let's call this dome upper, dome lower. I want it so that F maps dome upper into dome lower, okay? And now I'm going to look at the image of this whole thing. And then I'm also going to look at the image of the inverse of this map. Let's see. So it squeezes all of this stuff, so that maybe it squeezes it down to this. Okay. Now it's going to expand this thing, like this, and now I want it to wind and come back around. So the image is going to look like this. The image of the whole thing is going to look basically like this. There's going to be, the whole thing is called Q, so this is F of Q. Let me shade it. So f of q looks like.
We have various other colors if you want to use.
That's true. I don't even need good stuff, right? If I do it again, now it gets tricky. I'm going to squeeze this thing again. You know, I can think of sort of like a thickened version of this thing. What's going to happen? I'm going to double this up. I'm going to squeeze it around. Let's see if I can take a crack at a picture. This is the good one. Let's make it green. So this thing now is going to go like this. It's going to be squeeze it. I'll draw it just like with lines first, and then I'll sort of fill it in. Just thicken it. This is f squared. Let me also look at the inverse images of this mapping. The inverse images of the mapping. Well, okay, so the f squeezes it, so the inverse is going to expand it. I could use a different color, right? This is green. I could use black, perhaps. So let's see. So this squeezes. This is going to go basically like this. And of course, what I did for f squared, I can do for f to the minus 2, etc., creating more gradations. Let me look at a little corner up here after, let's suppose we look at, I'm going to focus here, and I'm going to look at f squared of q intersect f minus 2 of q up here. What is it going to look like? Well, there's going to be 2 of these in this direction, and there's going to be 2 of these in this direction. So notice that if I repeat this, it's looking like a Cantor set in the horizontal direction as I take more and more iterates, and also in the vertical direction. So what I'm thinking is the following, although I'll leave it to you to kind of examine it a little bit more closely. I'm going to define this set. It's called the non-wandering set. Omega. What did I call the first thing? S, the square. So let's call this F. take a look at this. Well, this is going to be invariant, because if I start out at any point here, it's going to keep going into these vertical and horizontal strips as I take the iterates, more and more iterates. This is invariant. That is f of q, f of omega, is going to be equal to omega. Just by virtue of its definition, it's going to take omega into itself. What is omega? Well, it's going to be the intersection of closed sets with closed sets. Omega is a closed set. It's closed and bounded, so it's a compact set. And what does it look like? Well, I keep doing 2-unit Cantor set types of things vertically and 2-unit Cantor set things horizontally. It's going to be equal to the Cartesian product of a Cantor set with itself. It's going to be a fractal. So it's strange. Is it an attractor? No, it's not a global attractor, but it is a forward attractor. Okay. So this is an interesting set. Let me look. Well, first of all, why should this be chaotic? As I said, whenever you have a transverse homoclinic orbit, you can kind of expect chaos. Well, let's see. What do I got here? If I look at the, green is bad, let me use that. Let me use red for the unstable manifold. This is a crappy red one.
Use my good red one.
This is a good red.
Yeah.
Let's see. So for the unstable manifold of this point, it goes around and around and around and around and around in the horseshoe. Okay, what about the unstable manifold? I'm going to look at the inverse image. This is red. Let's maybe make it black. Okay, so the unstable manifold, the stable manifold, okay. And suppose now I take the inverse iterates of that. Round and around and around and around and around. Bingo! There's your transverse homoclinic point. So just by the way this thing is set up, it has a whole host of transverse homoclinic points. But even with that, well, why is this thing chaotic? Well, you know, we looked at the intersection when you have a transverse, and you see a lot of wiggling and so on. It kind of looks maybe chaotic, but that's not a proof. All right, this is what I'm going to do. I'm going to look at F. I don't want to lose any of the good stuff. This is no good. This is just plain old regular stuff. This is good. Okay. All right, let me define the restriction of F to the horseshoe. There is a restriction because this is an invariant set. I can consider the map restricted to this. Let me call it F. Let me define it here. Well, let me set up a mapping and terms of something like symbolic dynamics. Let me define a mapping. Let's call it H. This is, by the way, something that's called a conjugacy. Let's set it up as follows. I'm going to set up a mapping from X in the Cantor set, omega, to double binary sequences. Not 2 to the natural numbers, but 2 to the z. What do the elements look like? Let's say they start, we'll represent them, say A naught. Let's say that's a starting point, A1, and then A minus 1, A minus 2, etc. So those are the sequences. Here's the way I'll define it. I'll say that let A sub k, and this be designated as H sub k of x. Okay. So that's going to be equal to 0 if f of k of x belongs to V0. Well, let me tell you what V0 is. This is V1. And 1 if f k of x belongs to V1. It's got to be one of the two, because this is going to stay on that Cantor set, so it's going to have to be all of the images as they go along is going to have to be either in V0 or in V1, because this is an invariant set. Okay. Now let's take the shift map. Not on 2 to the n, but on 2 to the z. The shift map takes minus 1, dot, A naught, A1, A2, etc. It moves the decimal one place to the right. That is the shift map. Let me compute for this definition 2 things. Let me look at sigma h of x, okay, or composition, and compare it with h f of x. Okay. So suppose I look at hk of this. What does sigma go? It takes hk into, let's say hk is equal to ak. So what is the left-hand side according to the shift? It's ak plus 1. As it shifts one to the right. What happens over here? Well, if I take hk of this, this means that f of k plus 1, it's f of k of f of x, belongs to V0 or V1. So this is going to be equal to a sub k plus 1, too. In other words, of course this is an invertible map. H f h minus 1 is just going to be equal to sigma. H is a homeomorphism. Let's set up. And what, I want to use a metric on omega. It's sort of consistent with the metrics I used in the symbolic setup. So the metric I use here with this thing, let's say x minus y, well, I can do, again, it's binary, so I can take a sub k minus b sub k over 2 to the k, and I'll let k range between minus infinity and infinity. That's a perfectly good way of representing points that are close in the square. Oh, okay. So, what have I shown? I've shown that f restricted to omega is equivalent to a sigma map to the shift map. Okay. So the dynamics of f restricted to omega are identical to the dynamics of the shift map. So what about it? Periodic orbits of all periods. Of all periods. Dense orbit. If you computed the Lyapunov exponents, you could show that the Lyapunov exponents are positive. It's chaotic, so f omega has periodic orbits of all periods. Has a dense orbit. As a matter of fact, if you take all of the periodic points in this map, because you're allowed to get any period you want, the closure is going to be equal to omega. So in other words, the periodic points are dense in this set, big omega. And there you have the chaos. So if you can identify a horseshoe, you know that it's going to be equivalent to a shift or a subshift. In other words, it may not be a pure shift, but some iterate of it may be a pure shift. It could be a subshift. And once you have the identification of this horseshoe, then you know you're going to have a chaotic regime on the set omega. So that's one way. I've used this technique in several cases where you take a look at a map, you think it's going to be, it looks chaotic. You look for some square that is going to be mapped like a horseshoe. If I can find for this, say, a planar map, if I can find something like a square, it doesn't have to be a square, so that the image looks like that, then you know you're going to have a transverse homoclinic point, you're going to have shift or subshift chaos. There you go.
I have a question. With the butterfly map, it's not going to really look like the horseshoe, right? Because isn't it going to like be like, isn't it going to be like all lines like throughout the whole map?
Well, no. Think of this not as a map of R3 into R3, but the Poincaré map of one of the recurrent orbits. So if you're, let's say, in the Lorenz setup, you've got this and this, and you got the two butterfly type things. So you've got this butterfly strange attractor. If you take a chunk of two surface in the right way, and you look at the first return map, sort of what I showed rather early on, you can find them so that you have something like this. You start out something like this. Let's say this is Q, and the FQ looks kind of like that. So you can actually identify horseshoe mapping behavior.
So if you zoom in on the attractor, there should be a portion that could resemble a horseshoe shape.
Yeah, absolutely. Yeah, and you see with the Idon map or this thing, it's sort of like that. It goes back and forth. As I say, it's sort of more like a boomerang shape than a horseshoe, but it has the same basic features. And you have the symbolic dynamics and all the stuff that goes along with it. Okay. So play with the